Hello everyone, and as your host, Dean Proctor. Today we're going to be going over another example problem. This example problem comes from Chapter 6, Kinematics of Rigid Bodies Undergoing Planar Motion. We're going to be looking at 6.1, the velocity of a pendulum. I don't actually have a grandfather clock, so I'm not going to be able to demonstrate what that looks like for you. But if you're a fan of the channel, you know that I do have this tennis ball attached to some fishing line. So we'll use this as an example. On this nice December day, we could pretend that this is a pendulum going back and forth. You know, everyone gets the idea. I'm sure you've seen a grandfather clock before. Obviously, if I was just doing this right here, it's going to eventually slow down and come to a stop, but a grandfather clock wouldn't. Okay, so we have our example problem set up from Chapter 6, Velocity of a Pendulum. We're going to determine the velocity of the pendulum's tip as a function of time. I have written here that the goal is to find the velocity of the pendulum's tip for any value of time. We're given the length of the pendulum and its angular deflection as a function of time. That's this right here. And I drew right here a simplified pendulum pivoted at point O with the tip at A. So as you can see, this would be like the tip of the pendulum. This is the top where it'd be swinging from, and up here would be like the clock. So to solve this, we're going to be differentiating theta with respect to time. So we're going to have this equation equal to omega theta cosine. Using 6.4, it gives us that VA, equation 6.4 from the textbook, equal to VO plus theta RAO. So this is equal to 0. Plus theta dot k radians per second times LER. So VA is equal to this LO cosine ET. And this makes physical sense. As a pendulum gets longer and it ticks at the same rate, we'd expect the tip's speed to increase, obviously. So, sorry, I was wandering off the page there for a second. Obviously, you know, if we have a longer pendulum, you know, a length of this tip is going to travel further distance. And since it's traveling a further distance, if we're keeping time constant, its speed is going to need to increase, because if you have a longer distance, you want to keep the time the same, you're going to have to increase the speed as well. So this equation accounts for that. It's going to make sense when we're looking at solving for the velocity of the pendulum's tip as a function of time. Hope this helps. Please like, comment, subscribe, and yeah, thank you guys. Thank you, Dr. Campbell.